Recording has started. All right. Well, good afternoon, everybody, and you're all very welcome. This is the presentation by the Institute of Refrigeration Ireland. And the presentation this afternoon is on thermal storage, optimizing energy use with ice thermal storage. Our speaker is Robin Verheyen from BAC in Belgium, Product and Applications Engineer. So Robin is going to tell us all about the technology of thermal storage, using ice for thermal storage. And the the presentation slides will be available after the webinar, and there'll also be a recording. And if you have any questions, there should be a bar at the top of your screen that says Q&A. If you just type in some questions there, and if we have time at the end, we will take a few questions. So I will hand over to Robin, and I'll hide my camera. Thank you very much. Thank you, Robin.
Okay, thank you very much. So I would like to start with introducing myself. So as said, I'm Robin Verheyen and I work as a product and application engineer at BAC. But first, let's have a look at who's BAC. So BAC is like a global company with decades of experience, especially in evaporative cooling towers. As a company, we strive to keep our position as a market leader today. And this we do with, of course, being a pioneer in different types of cooling now today, because the market needs different types of cooling. So that means that we are also the first that launched the adiabatic unit, but also the ice thermal storage tanks on the market, like you can see here at the bottom in our wide product portfolio. Important is that we are a global company, as you can see, with multiple factories and R&D centers, but still the goal is that we leverage local experience via our local sales team that is available in every country of Europe. And this keeps the local touch with you as a customer. So enough about BAC, especially about me. So let's now talk about ice thermal storage. So today we will be discussing ice thermal storage tank, and especially we will explore the application in which these tanks are used, so as well as how to design a proper ice thermal storage system. And at the end of the presentation, we will of course show the benefits in combination with some real examples that are practiced on. So an ice thermal storage tank, as the name suggests, can actually be compared as an energy storage system. And what is now a typical, very popular energy system that we have today? Home batteries. So you can compare ice thermal storage with home batteries. Only the big difference is, of course, that we are not using electrical or chemical energy to store but we will use a coil. And that brings us to the definition. So ice thermal storage is a process of using a chiller or refrigeration plant to build ice during off-peak hours and to serve as a part or all to the on-peak cooling requirements, as you can see here in the graph. So the blue one is off-peak ice making, where the red is indicating the period in an HVAC profile, for example, where you will discharge the ice. You will use the ice to reduce the chiller size. And that brings us to different reasons why to use ice thermal storage. So ice thermal storage, this method, ensures that your refrigeration equipment is no need to be longer designed for short peaks in the load profile, as you can see in the graph, but you can size it now for the smaller amount that you see over here. This will not only result in a smaller chiller size or standard refrigeration equipment size, but also in the amount of refrigerant that will be used in your plant. But there are more benefits, of course. As you can see, ice thermal storage is also a very efficient way to store energy or cooling. And this is because we will utilize the latent heat. In the graph, it is shown that the amount of energy required for a phase change per kilogram of water is quite high, as you can see, especially if you compare it over here, the red, with the blue line, the delta T that is needed for the water to store the same amount of energy as with latent heat. So as a result, we say that the storage volume with ice can be up to 8 times smaller compared than with with water storage over here. Now there are of course still more benefits to see. Another benefit is, for example, I'm now thinking about food industry. Ice can here deliver very cold temperatures, close to 0.5 or 1 degrees. This could be useful in processes where, for example, you need to cool down milk to a very low temperature, the pasteurization process. But of course, additionally, ice, we have last days a lot of green energy, and that is good. But of course, that means that green energy gives fluctuations on the grid, and also today, still our energy demand is continuing to rise. So this creates the need for a smart energy usage when the demand is low. And of course, some of the grid manufacturers are asking to reduce the consumption during peak periods. And the best way to maintain this and also to keep the user's comfort is of course by using a battery energy storage. This can be done with, for example, the electricity batteries that we saw and that we see today a lot, but you can also store it in a nice thermal storage tank for cooling. And of course, next to it, you can use, of course, this also as a backup system, because it's very important to note that ice storage does not reduce the total energy consumption, but it can lower the operating costs, of course, by potentially lowering the and by smart using the energy demand. And this is by smart using the energy when the tariffs are low. But on top of that, ice thermal storage will give you availability to have a backup system. So in cases where cooling sources such as chillers fails, or there is a power outage, ice can still provide the necessary amount of cooling. And this can be achieved with, for example, a basic pump that remains operational, and with some smart valves that of course control the amount of flow that is going through the ice tank. This could be very useful in critical applications like data centers or clean rooms or traditional HVAC systems and buildings. And all these benefits can be used in a variety of course, applications. And normally we split them in two big groups. We have one big group with HVAC applications where you have, for example, hospitals, airports, office buildings, but also the bigger ones, the district cooling, or of course the very critical installations like data centers or laboratories. And on the other hand, you have, of course, typical industrial applications like dairies, breweries, or like general process cooling. Now, let's take a deeper look in how to select a proper ice thermal storage tank. Before we begin, it's important to understand that in general, there are two types of ice thermal storage, internal and external melt. And the key difference lies in how the ice is melted. So let's start with internal melt. In this process, a cold fluid, such as water in combination with glycol, flows through the coil. This fluid has a negative temperature, for example, -6, which is needed to, of course, build the ice. Then the melting process will occur. With internal melt, this is a closed loop. So that means we will use the same coil as we build the ice to melt down the ice block. That means we start melting down the ice block from the inside, as you can see here in the drawing. And this you can compare with, for example, ice or let's say a bottle in an ice bucket, like in the picture. Now, then we have external melt. External melt is not a closed system because with external melt, we use the same concept to build the ice, but we are using, of course, a second circuit over here to melt the ice. And that is actually water that is in direct contact with the ice. As you can see on the schematic, the water is flowing really over the ice cylinder and is going into the tank. So you don't have a closed system anymore like with internal melt, but you have really an open system as you can see over here. The direct contact of water with the ice block in a second circuit. So that results that internal melt will deliver higher fluid outlet temperatures because of the barrier of the coil between a layer of water and of course the ice, means that it is more useful to use, of course, in processes with long meltout time. For example, a typical HVAC profile, as you can see below. Where with external melt, you have the real power of direct contact between water and the ice block, but allows you as a customer to have very short meltout times, than typical pasteurization processes, food industry, and also due to the direct contact with ice and water, you can have very low leaving water temperatures to 1 degrees or even sometimes 0.5 degrees. So that means as a conclusion, what we typically see here is that internal melt is used for HVAC applications with, of course, more a steady load profile or a small increasing load profile. And external melt is mostly used for industries like dairies, breweries, food industry, for example. Now, let's take a look to a typical HVAC application. So here you will see a typical HVAC application is quite a small increasing load. This with a long meltout time, you see between 8 and 18, so 10 hours of time, and typical water temperatures with, on the water side, 6 to 11 degrees. On the glycol side, other loop of the heat exchanger, typical 3 degrees, for example. That means the perfect solution here would be internal melt. A closed circuit, so we use the same coil to build as to melt the ice. Now let's have a look how this works. So as we discussed in a previous slide, we will first build the complete ice block via cold fluid going through the tubes, through the coil. Complete ice block is formed. And now we will pass water fluid, for example, 6 degrees, 11 to 6 degrees, through the coil, and we will start melting the ice from just around the coil, from the inside of the ice block to the barrier. And this we do till the complete ice block is melted down. Now, we will translate this in a typical internal melt schematic. As you can see over here, we will use a glycol chiller in combination or in series with an ice tank, still in combination with some bypass lines. But we will talk about it more in the next slide. So this is typical how we will build the ice. What we will do is we will modulate the V2 three-way valve. That is to prevent, of course, that the heat exchanger will not freeze. And then we will activate the pump and the chiller to deliver negative temperatures, typical -6 degrees, to the ice tank to start building the ice. So in the next slide, we will show you how to melt the ice when the ice tank is needed, of course. So cooling with the ice chiller, and of course, what you will see is that we will use chiller and ice tank in combination, and this is to make or to have the most efficient solution. So we keep, of course, the ice tank smaller by using the chiller still during the day. And of course, we place the ice tank after the chiller, because the chiller then only needs to provide higher temperatures, where the ice tank will definitely give lower temperatures because it's with ice. This gives a more efficient solution because also the chiller is not forced to deliver low temperatures, but can work on higher temperatures, but is more efficient. And what will happen is now the V2 three-way valve will be activated to pass the flow through the heat exchanger, and via the valve V1 on the right side, we will modulate this valve to be sure that the combination of the water coming directly from the chiller and the water that is passing after via the ice thermal storage tank gives a nice mixture temperature of, in this case, 3 degrees. Now, to give you some more insight about internal melt, mostly the typical fluids that are used are ethylene and propylene glycol. So when would you use ethylene glycol? So ethylene glycol will have a lower viscosity and is in general more efficient to use for ice thermal storage. But what we see is, of course, that it is toxic. So therefore, in a lot of food applications, you will see that maybe the less efficient propylene glycol will come back because, of course, it's non-toxic. So typical food industry, hospitals and school is propylene glycol. All the rest we see mostly with ethylene glycol today. Important is also that we see combinations of 25-30% ethylene glycol in water. Important to notice is that if you increase this percentage, of course, the efficiency will drop very sharply after 35% of ethylene glycol. Always take into consideration that there is enough ethylene glycol in your water mixture to prevent, of course, freezing when building the ice, because then you need negative temperatures, of course, to make from water ice. A typical internal melt tank is a tank where you have outside panels and, of course, a liner in the inside, because, of course, it's a closed loop. We will use the coil to build as well as to melt the ice. It's a typical galvanized steel tank, and also what we have here a lot is galvanized coils with, of course, continuous circuits. So no welds between the tubes, so a complete circuit. Actually, the same coil as or the same designs, same procedure to assemble a coil as with our cooling towers. And to measure the amount of ice, we use our sensor on the ice tank. This sensor will use, of course, the difference in density of water and ice. By changing from water to ice, you will see that the level of water in the tank will change because the density changed. Now, let's take a typical food application, for example. A typical food application, as you can see in the graph, is more with peaks, like the pasteurization process. You need to cool down a certain process in a very short time. For that, external melt is the ideal solution because high peaks and low temperatures you can have with direct contact between ice block and water. Even here on the drawing, you will see there is a bubbler system, but we will talk about more in one of the next slides. A typical schematic for external melt is this one. And here you will see already a slight difference between internal melt. With internal melt, we are using the same coil. It's general more easy to install. With external melt, you will see that you have two loops. On the left side, you will have the loop over here to build the ice. So the loop, the refrigeration of the glycol chiller connected to the coil with standard little bit lower temperatures, -8 to -4. And on the right side, you will see here the cooling load. The cooling load now directly connected to a pump that will force water going through or over the ice block in the tank. So two separate loops. So concept is the same as with internal melt to build the ice. We will build complete cylinder of ice around the coil by passing cold glycol, or in this case also refrigerant, through the coil. But melting is slightly different. By melting, we will start melting external melt from the outside. So the water will pass through the tank and will melt this cylinder from the outside to the inside. As you can see also here on the schematic. And at the end, of course, the same, we will end with a complete tank full of water. It's important to melt down your complete ice tank once a week, max 2 weeks. This just to prevent, of course, that some parts of ice will stay in the ice tank, and that later, when you start building again the ice, you have an uniform ice build, because this can give additional stretching or pressure on the coils. So that means a typical ice tank, an external ice tank, looks like this. Typical application or typical ice tank is a welded tank. Why? Not with a liner. The reason is because here you have additional connections because you have the loop of the water that is in contact with ice. So therefore, a weld will give a better insulation or prevent leakaging by passing water through different layers of panels. Now let's have a look into the inside of an external melt tank. So typically what you will see is here is in the middle and on the left and completely right side, but especially in the middle, you will see a gutter that will guide the water completely, the hot water that is coming into the unit, to the back of the unit. There it will be pushed against the wall, and then the inlet connection where the photo is taken through, this inlet connection will suck the water out of the tank and will force the flow going over the complete ice block. Now you see some small PVC pipings below. You see 3 on the left, 3 on the right, completely to the back. These are bubbler pipings. So here, and that's the special thing with external melt, what you don't have with internal melt. Here, we will push air bubbles, some air, in the ice tank. Why we do this? Actually, this is to have a proper heat exchange between water and ice, just to improve the heat exchange and to force, of course, the flow. So in general, now we saw 2 different types of installation, internal and external melt. And with external melt, you saw already in the slides that we have first ammonia, but also a glycol solution. We have both. Here you will see the difference in the coil. A typical coil, an ammonia coil, will have, of course, an oil purge. Where a glycol coil, you will see that we will equal distribute the flow between different circuits. I will explain it in the next slide. Here you will see it. You see the arrow? Here we indicate that we will pass flow to different layers of the coil. And why we do this? Because instead of with ammonia, for example, with glycol, you will see that there is a temperature difference when the fluid passes through the coil. You will see it here in the schematic. So it will enter with -6, but it will end and come out the coil with -3. That means that the LMTD, or the temperature difference, in the beginning between water and coil is bigger than at the end. That makes that the ice will not be uniform built, but will be more, instead of a cylinder, a cone. It's not really a big cone difference, but you see it. And therefore what we do is we regulate the flow through the coil. That, of course, we can optimize the surface of the cylinders or the cones that are formed. As a result, you will see in our selections that typical glycol execution will have slightly more storage capacity than an ammonia solution. Now here, you see a typical ammonia installation. Especially over here, it's an installation in Ireland for food industry. What you see over here is the BAC ice tank, but more important is, of course, the drum on top. A typical sign showing that we are using an ammonia application or refrigeration application. Now, let's have a look to a few installations. Here is one of our installations in Ireland, a newer one, in St. Stephen's Green. It's a typical HVAC installation. So a typical, we used over here internal melt tanks with a total storage of 2100 kilowatt hours. Also here, another installation, an HVAC installation, a building, where we even supported the customer to get his LEED Platinum certification for his building by using ice tanks. Ice tanks is, of course, not the complete reason for the LEED certification, but it's still a part of it. And this is because, of course, it is using the energy of the grid in a smart way. A totally different installation is, for example, Lee Strand Dairy. Here you can see the load profile. It's a pasteurization process. So that means that the milk needs to be cooled down in a very quick, fast way, resulting in high peaks and very short melt times. Here, no longer internal, but now external melt is selected, because due to the direct contact of water and ice, you will have these temperatures close to 1 degrees. And of course, you can melt down the ice block very quickly, very fast. And then we have another type of installation, a little bit bigger than the HVAC building type we saw in the beginning. This is a district cooling example. So what is district cooling? I think most of you are already familiar with this. But here with district cooling, we have one plant that is providing the heat and cooling for multiple buildings. It could be offices, it could be a mall, it could be hotels or houses or a hospital. So different applications. And this is how the network looks like. This is a network in Barcelona, and the project is called District Clima. So this network in Spain will have a quite bigger total storage capacity of around 120 megawatt hours. So that means actually a lot of coils are installed. And that's a very important point. In the previous slides, you saw actually that a lot of drawings are made with ice tanks, complete tanks, the coil into a tank. But for bigger applications, is what we see is actually coils stacked on each other and lifted into a concrete tank. This allows you to have much higher storage capacities in a small footprint. Because to give you an indication over here, you will see a lot of coils in 3 different concrete separate basins. And after here, they close it and they make a nice piece of nature in the middle of Barcelona center. Now, why they choose for ice thermal storage over here with the district cooling plant? Actually, it gives different benefits. So we saw it already before. You need to size not your chillers for the peak, but now you can actually spread the peak. It's also better to spread your energy usage. But in addition, what you see with district cooling plants is that the delta T is bigger. And the delta T means that also the piping can be smaller because the flows through the piping will be smaller as well. This is an additional cost savings that comes on top of smaller pumps, piping, air distribution systems. So this is an additional saving that forces the customer to go to ice thermal storage tanks. And then, of course, another very nice project to mention is, of course, the Burj Khalifa Mall. So here we provided, again, different coils, not tanks, but coils. We have even the largest capacity in history, 140 megawatt hours of ice thermal storage tank. Here important is to notice that it's not only serving the Burj Khalifa, but also the surrounding malls. So it's actually a combination of an office and hotel cooling, but also actually a mall or district cooling plant. So that brings us really to the end of the presentation, and I would like to summarize some key takeaways for you. So important here is that ice thermal storage will give you the benefit to shift cooling to off-peak hours. So in a smart way, you can reuse your peak electricity usage. Your size of refrigeration equipment will be smaller, and it can give maybe some additional cost savings. Also, as a customer, it will give you some flexibility in applications. This, of course, with also some low maintenance costs. Also, the ice thermal storage can lead to additional lead-friendly buildings. And of course, it's an additional backup to your system. Because remember, when your chiller switches off, can be an issue, can be maintenance, the ice thermal storage tank will be there. Also, the ice thermal storage tank will not have a lot of components that need to be maintained, so less maintenance is needed on this tank. And you see in the pictures below, ice thermal storage is already a proven success in different types of industries. So in general, do you have an HVAC application, for example, or you have process cooling, pharmaceuticals, breweries, pasteurization processes, or you have a data center, it's definitely something to look into. So I would say, if you have questions, don't hesitate to contact our sales guy in Ireland. It's Joe. He's on the call over here. Here is, of course, his email address and the number. Don't hesitate to contact him or, of course, me. We are always here to support you with more technical questions or to plan an additional meeting with some additional information when you require more info. Okay, thank you very much for listening. And I'm now here available for some questions.
Okay, well, thank you very much, Rob. Rob, that was an excellent presentation. So we'll see if any questions come in. Maybe they're coming in the chat. Just one or two from me. One is, what's the life expectancy of an ice bank, Robin? How many years should it be expected to last for?
Oh, actually, a nice thermal storage tank can be there for a lot of time. What we typically see is 20 years is very, very common in this one. And why is this? Because actually, with ice thermal storage, you have less or no moving parts. So with external melt, you have the bubbler system, but for the rest, you have all steady parts. You have a coil. So with some proper maintenance on the water on the unit, regular check, you can keep him there for long. Especially, I was looking now with my sales guy Joe, and we saw an ice thermal storage tanks from 1995 in Ireland still up and running. So that's quite a nice example.
Okay, and the refrigerant. You mentioned that there can be refrigerant or ammonia, which obviously a refrigerant. What temperature, what evaporating temperature is needed to build the ice on a direct refrigeration system?
Mostly what we see over there is something like -4, -5, for example. But depends a little bit. So there we support customers, of course, with a detailed simulation. Why we do that? Because there are different ways to size your unit to have maybe a smaller installation, or you can increase the size to bring up, of course, your temperatures needed to build the ice. This by then, of course, building smaller layers of ice. Because typically what you will see is that the more layers of ice you are building, and the bigger the cone or the cylinder is becoming, the lower the temperatures you need for building the ice.
And at full cone dimension, then would -4 degrees still do it, or do you need to be colder, evaporating at a lower temperature?
Yeah, at the end you will see that you need -6, -7, for example. Yes.
And in terms of the after the battery, if you like, has discharged and the ice has all been used up, does the ice bank continue to provide chilling, or is a separate chiller needed?
So actually depends on how you will use the unit. So you mean an additional chiller to build the ice, or in combination with the unit?
Well, in combination. I mean, would a typical installation only have an ice bank, or would it have an ice bank and a chiller?
Yeah, mostly what we recommend is a combination of both, because you will use the chiller to build the ice, and you can reuse this chiller during day, of course, to support the ice tank, or actually the ice tank will support the chiller. Why we recommend this? To have, of course, a smaller ice tank, but still there are some applications where there is only ice available during day, and it's not allowed to use a chiller because of its high energy demand. In that case, of course, you will have a nice thermal storage tank doing all the work during day. But typically, we use the combination of a chiller, and after the chiller we place with, for example, internal melt. After the chiller we place the ice tank, because the chiller will provide a part of the cooling and the ice tank will give them the boost, the extra peak will deliver the ice tank.
Okay, thank you. And then the last question for me, if anybody else has a question, just type it into the chat or the Q&A. One contractor I spoke to before the presentation said that they're very happy on the refrigeration side of things, but they're not too comfortable on the chilled water side of things. So the delivery of chilled water and integrating ice banks with chillers and storage tanks and pumps and so on. So the question would be: is there any support available from BAC for the design of a system as opposed to just the supply of an ice bank?
Yeah, so actually as BAC, we will not design a complete system with controls and everything in it. We will not do the complete design, but we can of course support during meetings some people that are working on this one with our tips and tricks.
Okay,
so the design
terrific.
is not in our scope, but the support we will always deliver where we can.
Okay, terrific. Okay, so just a final opportunity then. Does anybody have a question that they want to raise? If you want to just flag it. Okay, well that's fine. So we were aiming just for less than an hour, so we're doing well, 40 minutes. So once again, thank you very much, Robin. A very good presentation. It's very nice to have the slides, and we'll have the recording as well on the website for anybody who wants to access it. And then just a heads up on our next webinar is on the 12th of March. It's a talk on optimizing performance in heating, ventilating, air conditioning, refrigeration with motors and drives. So the presenter is Chris McGurn from ABB Motion. So the talk will be on the use of inverters or VSDs in refrigeration and air conditioning applications. So the details of that are on the website. It's on the 12th of March, and I think it's at the same time, 1 o'clock. So again, thank you very much, Robin, and thank you all for attending. And have a good day. Thank you very much.
Thank you. Enjoy your day.